to environmental condition, provided they are very exposed for a very long period of time. But the issue is, but the issue is, uh, it takes a lot of time. Means a minimum of 100 hours of testing. So, and for a testing which can go up to like 3 years or 4 years, when you try to find out what will be the residual strength of a material or a particular FRP component, if and whether they are going to, if it is going to be extended or exposed to the environmental condition for a very long period of time. So I actually, when this offer was made to me, I was working in ITM University, but now I have switched to NAMTech, which is currently running in the campus of IIT Gandhinagar. Okay. So AI ML is a large field, very vast field, but as we know, all of these models cannot be used for our application in composite science and technology. There is very limited number of models which can be used for our property prediction, or whether the model can be used to tell us whether the component is going to survive, how long or how much time it will take for a certain amount of property to be degraded to a certain level, right? So there is a difference between how an AI ML code is made and what is the difference between our general programming. So not, no, not going, sir. Ah. So sorry. So this is how actually what is the difference between our regular and machine learning algorithm. For a regular algorithm, if you try to write a computer program to predict the mechanical property of a material after a certain period of time, we require to write the steps involved in predicting that property. But on the contrary, a machine learning program extracts the relationship between different properties using the data itself. So this is what this image is trying to explain. So machine learning program or coding has this inherent ability to extract the reason or relationship between different properties. So when it, why machine learning, or whether we can apply this machine learning for property prediction or not. So machine learning is all about writing a code in such a way that the computer becomes smart enough to tell you how much property of FRP composite is remaining with it after a certain amount of time has been spent during its service life. So, but the problem with applying a machine learning model in our FRP composite is grave. First of all, the FRP properties vary from people to people. Same amount of materials, same manufacturing property. Manufacturing process. If two different person are going to make a certain component, definitely the properties of that material is going to vary. So it is a challenge. Plus, why machine learning? It's a computer-based reliable method. Means if you are using implementing a computer, the biasness is not there. Means you will not be able to manipulate the result which is coming out of the computer, right? Offers great flexibility. All you need to do is to change the label of the information, and the machine learning model will help you get that to the property. So it can basically help us cut down the cost which we spend in testing of material, and all it requires is the data which is available in the literature for industries, which is the data available with them, and they can use it to predict the final property of a material. But what is the problem? The challenges is the machine learning model requires a very large amount of data. The work that I'm going to show you is based on 2000 or 2900 data points. But if you have the data points more than like 10,000 or 1 lakh data point, the machine learning model is work superb. And that is the only limitation with machine learning model. So it's quite important that person or people from different domain come together, share their experimental data to make or create a machine learning model which is robust enough to satisfy your requirements. Heterogeneous sources means the data that I have used is from different sources, different articles. So obviously there will be non-homogeneity in the data. Domain shift between lab and factory. Some data was taken from the factory data, some data were taken from the laboratory conditions, and that is why. But machine learning model again has the ability to help you normalize all those data in terms of computer programming. So class imbalance and defects, because most of the literature that you are going to study, they are not going to give you the details of what is the void fraction of the composite, what was the route that you used for the manufacturing of the composite, what was the curing temperature, what was the ambient temperature, like this. But as a domain expert, as the person who is working in the field of composite material, it is important to understand, because you understand what are the important features that control the output of a given component. So just I'm showing you this kind of data right now on the screen. We can see there's no label in the data, but those sitting, I also know that we can see a general trend in the data. As the numbers on the left is increasing, the numbers on the right column is decreasing. So this data is unlabeled. It can be anything. It can be Taylor's tool life diagram, data from Taylor's tool life, or it can be a fatigue life diagram. But remember one thing, machine learning is never used for this kind of simple task. The task has to be means there should be large number of inputs, so that a human brain fails to correlate between the relationship between them. And this is why machine learning model comes handy into it. So if I'm going to increase the number of columns, some of you will start getting out what is the relationship between these two columns. And then again, I further increase the number of columns. And eventually I put so much of data that me as a human, you as a human will fail to understand what is the relationship between these two data. But remember, machine learning model understand these data and help you generate a model which will give you the required answer. So what in the backdrop, what machine learning does, it makes a number of iteration, maybe millions and billions of iteration based on the number of data that you have given, and it will come up with a solution. And we don't need to know about how many iteration computer has. They make it in the backdrop of the calculation, and all we need is to make sure that the answer it is giving to us is correct to the best of our knowledge, because we compare the results from emanating from the ML model with the knowledge that we possess. And once we find out that the result which is given by these model is correct, then we can successfully imply those model in our machine learning model. So when we try to, or when we attempt to predict the residual mechanical property, it can be anything. It can be strength, it can be stiffness, it can be strain. And this talk is all about understanding what kind of suitable predictor means, whether we can target to estimate the residual strength or residual strain or the residual stiffness when it comes to implying the machine learning model in the. So these are the 6 steps that we generally go through when it comes to machine learning model. Problem definition, what kind of data do we have, what kind of evaluation criteria we are trying to put, what are the features of the data, and what model should we use. But what I have done in this work is I literally applied every machine learning model which is available there. So like 10, 11 models I have tested, and their grid search version means modified version was also tested. So problem definition is for us, since these are based on numbers. So regression, which is supervised kind of learning, was there. So supervised learning and regression was the problem that we are trying to cover here. So data and features. So when we deal with data, data can have two terms. One, like I showed you in the table, it can be purely numerical, which we call as numerical feature. But there, like if suppose we are using CFR and GFRP, these are called as categorical features. So computers are not very good in interpreting these names, but they are very good in interpreting numbers. So what we do here, we use one hot encoder, and what it does, it converts those categorical features into the numerical feature deemed fit for the machine learning model. So that kind of Excel sheet that I showed you is, in terms of machine learning model, it is called as structured data. And if you are using some images or some acoustic signal, those are unstructured data. So my talk of today is based on structured data. So I'll be keeping it short on machine learning model, right? So this decides what kind of model we are going to imply, whether we are going to imply deep learning or we are going to imply machine learning. So since the data that I have gathered over the period of time was based in tables or Excel sheet, so machine learning was the model that we used. So as I told you, there are two different categories. One is numerical, one is categorical. Categorical does not contain number. And if you put these names in the machine learning programming, the computer is going to discard it. All it requires are numbers. So one hot encoder is given as an input so that these names can be converted into suitable numbers. So this is the number of features. On the left, 14. I have used 14 different features to predict the residual strength. So here we can focus that what was the saturation moisture content, 0.99%. Test duration was, it was minimum 336 hours was the duration. The maximum was 21,900 hours of testing. So all these factors contributed to the extent of degradation that the composite material witnessed when they are exposed for a certain period of time. So R square, MAE or mean absolute error, median absolute error, and root mean square error is the general statistical terms that we use to quantify the result or outcome of our machine learning model. So one thing we have to make sure that at least the data we are using in a machine learning model, it should be present in at least 10%, more than 10% of the rows of the data. Unless that is not happening, the machine learning model will not be able to trap the relationship between those important input features. So modeling, once we have decided what kind of data do we have, what kind of work we want our machine learning model to proceed with, then comes the selection of model. So selection of model, problem one, it can be a structured data, so machine learning model, or if you have images, sound, some thermographic images, or some resin flowing images that you want to implement to learn about how the quality of the composite is going to get controlled, we can go for deep learning model. So unlike conventional computer program, we do not need to write ML model from the scratch. To our luck, most of these models are easily available in the public domain, and what you can do is download it from the internet and start working in the model itself. So choosing and training a model, first the three steps are training, validation and testing, and then comparing the model whether one model worked good or not. But remember one thing, no one model is perfect. Your step is to use all the model, test all the model, and then coming up with a solution is working great for this particular kind of data. So coming to the results section, this is splitting up your data in validation, training, validation, and testing. But I would like to draw the attention to the results part. Right. So coming to the result part, this is how the machine learning model presents itself the data. Once you put the data, it tries to develop a scatter. It can be a bar graph also. How the target feature is varying when it comes to different input parameters. So this is for strain data. Strength. The next one, these two are for residual strain and residual modulus. Means I tried to find out of these three predictors, which one is going to be the most suitable, so that we get not the accurate answer, but answer which satisfies our condition, our requirement. This is called as a Pearson graph, and it based on the data itself. This is basically not how a machine learning program or computer is seeing at the data. This is actually, I want to see what a computer is trying to see. That is why we generally make this kind of graph. And it relates between the different input parameters. Here we can see the yellow lines. The residual strength MPS 0.92, it clearly understood that it is related with the strength. Higher the strength, the higher the probability of the residual strength. And this is how I did not write any kind of program to make them understand. The machine learning program understood this with the data itself, right? So talking about the results, here I have highlighted few results which is important to our nature. Fit of the data. TT is the decision tree model which had the fit of 0.96, which is the highest among all the tested model that we have done. And again, there is a model which is called as SVR, support vector regression. It has a negative fit, means it discarded the relationship between the data. And that is where the hyper tuning comes into picture. Once the SVR model was hyper tuned using grid search and cross validation, you can see that the fit moved to 0.88. Tremendous improvement from the previous result, right? Again, the same thing for the strain, and you can clearly see none of the fit in the data reached to a scale of our residual strength. So we can understand from this result itself that strain is not a very suitable predictor when we try to implement a machine learning model in the prediction of property. We should go for strength, or let us see what is the result associated with the stiffness. So here is the result associated with the stiffness 0.9805, 0.9842, 0.9769, pretty high compared to our strength, residual strength, and residual strain data. So this gives us a brief idea that if we are trying to implement a machine learning model to predict the residual properties after a certain period of time, we should not go for the strain property at least. Go for strength property or go for stiffness property, and then you will have the answer which will be suitable to your problem. Okay, so this is the Grid search CV means what is the cross validation score. So generally we try to have this score very high. Means this table shows you how generalizable was the result coming from different machine learning model. Higher the numbers, better the model. Means generalizability means how well my model is going to work when some unseen data is fed into the system, because we are trying to predict something and you will be preparing your own input data. So if sudden new data is given to it, whether it will be able to generalize that kind of learning what it has attained over the training module, so it can be associated. So this result is associated, can be associated. So once hypertuning is applied, different models try to hypertune its input, how it train itself in a different. And actually I'll share all this slide with Singh sir, so that, and I have the manuscript also, which you can go through and you will find out that each model treats different input parameter differently, and they have a number of hyper parameters which needs to be tuned in order to get to the right result. These are the results from the best model, each model which is having the best output, which is giving us the best output, right? And these are the heat map of input feature was kept at the priority. So we can see in the stress feature, particularly all model did not converge on a single module that strength should be the main priority. But when it comes to stiffness, result emanating out of for the stiffness, we can clearly see almost every model supported each other, that the residual stiffness should be the prime input feature which should be there in order to predict the residual stiffness of the material. So these are the graphs associated with the prediction model. So blue dots here shows you the SVR, support vector regression. When a model, machine learning model, discards the data, what it is going to do is going to predict some random numbers which is not associated or aligned with the input data given to the particular task. So every model is there, but it takes a lot of time. No one model is perfect. Remember one thing, if you are trying to implement machine learning, you need to keep this in mind. No machine learning model is final. No machine learning model is great. It may require, it may vary depending upon data to data, and a great amount of experimentation is required so that you can narrow down on the machine learning model which can help you get the required answer. So conclusion that I can draw, that not all the models, I told you, not all the models are capable of supplying you with the answer which is deemed fit, but at the same time trial and error is the only thing go for when it comes to finding out the result. There are like 10, 12. If you include deep learning, there is like 15, 20 different kinds of model. So as a machine learning enthusiast, as a machine learning engineer, it's your responsibility to test all the data, test all the models before you finalize or narrow down on that this kind of data is final to my work. Or suppose you can start outsourcing that software to different composite manufacturing industry, so they can have the brief idea that what kind of end property they are going to get when it comes to fabrication, when it comes to property degradation over the period of time. And that can be a great project for people working in the field of masters or doing masters from this Ahmedabad University. This can be a final year project for you guys, working on a data, developing a machine learning model, and then selling it to the industries so that they can come up with a final answer. So if based on my result, I'm just going, this is the last. If generalization means ability of a model to make a prediction even on the unseen data is the case, then BRR or ridge regression, Bayesian ridge regression, RAB is uh, I just it is a regression model. Then GBR is gradient boost regressor. They can be your model of choice. But when changes, the requirement changes from generalizability to fit, then our decision tree, support vector regression, and GBR or gradient boost regression is the model that you should go for, provided you are fixing residual stiffness as the suitable predictor. So we are, as I told you, Namtech is a new university. It is running in the campus of IIT Gandhinagar right now. So these are my details. If someone is interested, we can have further talk or about the future of this work in terms of composite industries as well. Thank you. Thank you for that.
Please. Thank you, Dr. Anand. So correcting that you are now part of NAMTEC. I would request